This is the third in a series of videos that I'm making to support a course in number theory that I'm teaching. And today we're going to talk about divisibility. So let's jump into the definition. So we want to suppose that a and b are integers and a is not equal to 0. Then we say one of these three things, which are all the same. We say that b is divisible by a divides b, or b is a multiple of a, if there exists some integer n such that b equals a times n. So let's look at this. We've got b is a times n. That makes b a multiple of a. But then likewise, if we were to divide a over to the other side, we see that b divided by a is an integer. But that's kind of the same thing as b being divisible by a, or saying that a divides b. So just to reiterate, these are three ways of saying the exact same thing. Furthermore, we have the following written notation, which is a with a vertical line and then b. So we read that as a divides b. So here's a little bit more notation. If a does not divide b, then we say a does not divide b, and we write the same kind of thing, except there's a line through that vertical line. And so that's read a does not divide b. Then I actually don't know the terminology for this, but we put two vertical lines and say a to the nth power divides b. Like I said, I don't know the terminology. If a to the m divides b, but a to the m plus 1 does not divide b. So what we've got going on there is m is the largest power of a that divides b. So this is sometimes interesting because if you're looking at the number 40, for instance, 2 divides 40, but that's not really giving you all of the information. The largest power of 2 that divides 40 would be the cube, because that would be like 8 times 5 is 40. So that would be a good place to see that. Okay, so now let's go through some assorted examples. So I want to notice that any number divides 0. So we can write that example as a divides 0 for all integers a, as long as a is not equal to 0 itself, because we can't like divide by 0, but we can divide into 0. So why is that true? That's because 0 is equal to a times 0, regardless of what a is. Okay, well, let's run through some other examples. Maybe that one that I just said verbally. So notice 2 divides 40. In fact, 4 divides 40. But maybe we would write 2 cubed double divides 40. And that's because 2 cubed divides 40. Because what? 2 cubed times 5 equals 40, but then 2 to the 4th, which is 16, obviously does not divide 40. Okay, well, we can also work with negative numbers. So maybe we could say negative 5 divides 30, and that's because 30 can be written as negative 5 times negative 6. Furthermore, like 12 divides negative 84, that's because negative 84 is equal to 12 times negative 7. Okay, so as you can see, these examples are fairly simple, but I think it's nice to have a careful way to talk about divisibility. Okay, let's maybe get rid of this and we'll prove some basic claims. Okay, so let's start off with a pretty simple claim, and that is starting with natural numbers a, b, and c. Those are arbitrarily chosen, although we will put some constraints onto them as we move towards these results. A divides a. So that actually makes divisibility reflexive. Next, we see that if a divides b and b divides c, then a divides c. That makes divisibility transitive. And finally, if a divides b and b divides a, then a is equal to b. And that makes divisibility anti-symmetric. And putting these three things together, that makes divisibility a partial order on the natural numbers. So that means that you can compare some natural numbers between this divisibility, but not all of them. In a total order, like less than or greater than or equal to, you can compare any two elements from the natural numbers. But of course, like with this divisibility, you can't, for instance, compare 5 and 8 just with divisibility. Okay, so let's maybe get to the proof. I'm not going to do this first proof because it's super simple. A divides A because A is equal to A times 1. So let's jump into this second one. So let's suppose A divides B and B divides C. So that tells us that there exists integers m and n such that B equals A times m and C equals B times n. So this is from the divisibility of B by A, and this is C by B. Okay, so now notice that we can take this expression right here and insert it into our second expression. Let's see what that gives us. So we have C is equal to AM times N, associated like that. But let's recall that multiplication is associative, and so that's equal to A times MN, but that's exactly what we need to say that A divides C as needed. Okay, so now let's move on to this second dot, which is this anti-symmetry. So let's go ahead and suppose that A divides B and B divides A. So this is a separate proof, so A and B have been reset. And then that tells us that there exists, I'll call them X and Y this time, which are integers, such that AX equals B. That's what we get from this. And then BY equals A. That's what we get from this. So A dividing B means that B is a multiple of A. B dividing A means that A is a multiple of B. Okay, so now we want to mash these together. So let's maybe take this expression for B and plug it in here, and let's see what that ends us up with. So that's going to end us up with A times XY equals A. So I did the associativity there. Okay, so where can we go from here? That tells me that A times XY minus A is equal to 0. Okay, but then that tells me that A times XY minus 1 is equal to 0. But then since A is not equal to 0, that means XY minus 1 is equal to 0. But we can actually argue up here that X and Y don't come from integers, they come from natural numbers. That's because A and B come from natural numbers. But that means that X and Y are both equal to 1. So X equals Y equals 1. Plugging that back over here, we see that A times 1 is equal to B. In other words, A is equal to B as needed. Okay, so let's maybe get rid of this and we'll keep looking at divisibility. Okay, so let's look at this next proposition. So we want to suppose that A, B, D, X, and Y are integers, non-zero as needed, so that divisibility makes sense like our definition over here. Then we have the following 4 results, which we'll take one at a time. So if D divides A and D divides B, then D divides AX plus BY. So notice X and Y are free in that setup. So let's maybe do this one first. So let's suppose D divides A and D divides B. So that tells us that there exist integers m and n such that A equals dm and B equals dn. So that's the definition of divisibility. Okay, but now let's calculate AX plus by, and notice that is dmx plus dny. We can factor a d out of that and see that we get d times mx plus ny. But now notice that's d times some number. But if that's d times some number, that means d divides this object right here. By the definition, we have d divides ax plus by. Okay, so that means we have taken care of this first purple dot. Now let's look at the second purple dot. If d divides a, then dx divides ax. So moving on to that, let's suppose d divides a. So that means there exists some integer m. I'll reuse the one from above. We've like reset our integers here, such that a equals d times m. Now we'll just multiply this entire equation by x. That tells us that ax equals dx times m, where I've commuted things as necessary. But now reading that off, that's exactly what we need to say dx divides ax. Okay, so we've proven this second purple dot. Now let's look at this third one, which is actually the converse of this second one. So let's suppose dx divides ax. So that means there exists an integer m. Again, we reset our integer such that ax equals dx times m. So that's the definition of divisibility for dx dividing ax. But now we need to do a little bit of work to get that d divides a. Let's maybe see how we can do that. Maybe we'll move the dx times m to the other side of the equation. That'll give us ax minus dxm equals 0. Okay, but let's see. That tells us that x times a minus dm is equal to 0. Okay, but that tells us that either x is equal to 0 or a minus dm is equal to 0. So let's maybe notice that x is not equal to 0. How do we know that? Because these things are non-zero as needed. And if x were equal to 0, we would have 0 divides 0 here, but that's not allowed over here. Notice the thing that is to the left of the vertical line is not allowed to be 0 in our definition. So since x is not equal to 0, that means a minus dm is equal to 0, which means a equals dm, which means d divides a as needed. So that means we've proven this third purple dot. Okay, let's maybe get rid of this proof and we'll focus on the fourth. Okay, now we're ready to look at the fourth part of our proposition. That says if d divides a, then a divided by d divides a. Obviously, we've got to use some of our knowledge of the arithmetic of rational numbers here, but I don't think this is much of a stretch. It's pretty clear what a over d means in this setting. So let's go ahead and suppose that d divides a. So that means that d divides... So that means that a equals d times m for some integer m as needed. Okay, but let's see, what is that integer m? Well, if we divide both sides of this by d, which we're allowed to do because we know d is non-zero, because everything's non-zero as needed, we get that m is equal to a over d. Now, this looks like it's happening in the rational numbers because it's a ratio of two integers. But given the fact that we know that m is an z up here, this is okay. But now we take this expression for m and plug it into that expression involving a and d, and we see that we have a equals d times a over d. Okay, great. But now, reading this as a equals a over d times an integer, that's exactly what we need to say that a over d divides a. Okay, so that finishes off the proof of this fourth part of the proposition, and thus the whole proposition is proven. Now let's get rid of this and we'll keep going. So our next big result is called the division algorithm. And this kind of answers the question, well, what if we don't have exact division, but instead we have division with remainder? That's what we're getting here. So we want to suppose a is an integer and b is a natural number. Although this can be tweaked so that b is an integer as well. I'll let you guys think about how to do that. Then there are unique integers q and r, quotient and remainder, such that a is equal to b times q plus r. But if you remember anything from grade school, you know that the remainder is bound between 0 and b, which is the divider. And it can't be equal to b. It doesn't make sense to divide by 6, for instance, and keep a remainder of 6, because you would just like get one more in the quotient. Okay, so let's maybe jump into the proof of this, which involves looking at an interesting set. So let's consider the following set, which I'll call A. So this will be the set of the following form: A minus bx, as x ranges over all integers, but then we're going to take that and intersect it with n. So A is the intersection of this set and the natural numbers. Okay, well, before we really jump into a proof, what I'd like to do is do an example of this set with specific values of A and B. So let's maybe say that A is equal to 14, and then we'll say B is equal to 5. Okay, so in that setup, our set A is equal to, well, let's see, 14 minus 5x, as x ranges over all integers, and then we're going to intersect that with the natural numbers. Okay, so let's see. I'm going to draw this for our set described like this in set builder notation, then we'll intersect it with natural numbers. Now let's see, I'll write some integers above here just to keep track of where we are. So let's say we've got 0 here, 1 here, 2 here, and 3 here. And then we've got -1 back here and -2 back here. So just to reiterate, this is just some bookkeeping. Those are my values of x. So let's see, if x is equal to 0, well, that's easy. I get the number 14. Now, if x is equal to 1, I get 14 minus 5, which is 9. If x is equal to 2, I get 14 minus 10, which is 4. If x is equal to 3, I get 14 minus 15, which is -1. And then notice everything to the right of that is negative. So when we intersect with natural numbers, we actually don't need to worry about that. Now let's move in this direction. So if we plug in -1, I get 14 plus 5, which is 19. Plug in -2, I get 24. So now let's see, I intersect that with the natural numbers, and I get 24, 19, well, this goes on infinitely. 14, 9, and 4, and then that stops. Now let's look at this. If I were to just divide this from what I know from grade school involving quotient and remainder, I would write 14 as 5 times 2 plus 4. In other words, 14 divided by 5 is equal to 2 with a remainder of 4. That's kind of a more standard way of writing it when you're a kid. Okay, well, notice that this remainder is in fact the smallest element of our set A. So that would be our R. And what's the x value that goes along with that? Well, that would be this number right here, and that turns out to be the quotient. So seeing this really gives us an idea for how to work with this set in order to construct these numbers Q and R. Okay, let's get rid of this example and then we'll do the proof for real. Okay, let's get going. Recall our set capital A was A minus bx as x ranged over all integers intersected with the natural numbers. So I first want to claim that A is non-empty. This is actually pretty clear from our example, but could be a little tricky to write down. So the way to do this is to take x equal to negative the absolute value of A minus 1. So this might seem a little bit overkill, but this actually produces a nice way to show that this is non-empty. So if you do that and you plug it into A minus bx, that's going to give you A plus b times the absolute value of A plus b after distributing everything. Okay. But now, since b is a natural number, it's bigger than or equal to 1, which tells us that this bit right here is bigger than or equal to 0. If a is negative, then it in fact might zero out, but otherwise it'll be positive. But this b being a natural number means that it's bigger than or equal to 1, which means the whole thing is bigger than or equal to 1, which means the whole thing is also a natural number. So by its form, it's in this set, and then by our construction, it's a natural number. So we're good to go there. Okay, so what do we have? We've got a set of natural numbers that is non-empty. That means it has a minimal element. So let's let R equal the minimum of A, so the least element. So that exists by the Archimedean principle. And Q is such that R is equal to A minus B times Q. So if R is the minimum of A, well, again, by the Archimedean principle, that means that R is in A, which means it's of this form. There is an X that makes this happen. We'll just call that XQ. Okay, but now notice that that tells us that we have A is equal to BQ plus R. So that got A written in this form, and now we want to show that R lies between 0 and B. So let's maybe put that as a little subclaim. That is, R is between 0 and B. And we're going to prove this subclaim by way of contradiction. So let's suppose that R is bigger than or equal to B. But let's notice that that means that R minus B is bigger than or equal to 0. But then we can look at the following calculation. R minus B is the same thing as A minus BQ minus B, which is the same thing as A minus B times Q plus 1. But let's notice that that is in our set A. And how is that in our set A? Well, it's in our set A because it's been written in this form and it's a natural number. Well, here I guess we're taking 0 as a natural number because R minus B is bigger than or equal to 0. But let's see, we've got R minus B is in A, but R minus B is less than the minimum value of A. But that contradicts the minimality of R and finishes the proof of this claim. Okay, so there's one last thing to do, and that is prove the uniqueness of Q and R. So let's jump into that. Okay, all that's left to prove for this theorem is that these integers Q and R are unique. So let's suppose that we've maybe got two of them. So let's suppose that A is equal to BQ plus R, and A is equal to B times Q prime plus R prime, where potentially Q and Q prime are different and R prime are different. Now, without loss of generality, we can assume some sort of ordering between R and R prime. And so you could really assume it either way, but the way we'll assume it is that 0 is less than or equal to R, which is less than or equal to R prime, which is strictly less than B. But that tells us that R prime minus R is strictly less than B and bigger than or equal to 0. So if you subtract two numbers that are less than B, and you take the smaller one away from the bigger one, well, you're clearly going to be less than B. Now let's also point out that this ordering on R and R prime implies like the opposite ordering on Q and Q prime. So this means that Q prime is less than or equal to Q, which tells us that Q minus Q prime is bigger than or equal to 0. So now we're ready to go. Let's start with this inequality. So we've got B is bigger than R prime minus R. But now moving some things around, we see that R prime can be rewritten as A minus B times Q prime minus R, which can be rewritten as A minus B times Q. The A minus A's cancel, and we're going to be left with B times Q minus Q prime, where some sign changed because of these double negatives. Okay, but now we can divide both sides of this by B, and that will tell us that Q minus Q prime is less than 1. But then this over here said that it was bigger than or equal to 0. And recall that they're both integers. So we've pinned a difference of two integers between 1 and 0, but that means it's equal to 0. So we've got q is equal to q prime. But then pushing that up through the rest of the equations, that tells us that r is equal to r prime as needed. Okay, so let's get rid of this, and I'll leave you guys with a couple of exercises to practice these ideas. Okay, so let's finish off with some exercises. So if you're just following along for fun, these would be great places to start to extend your knowledge, although you'll probably want to look for some other exercises if you want to continue to practice. If you're in the course that I'm teaching, then you'll need to turn these in at our next meeting. Okay, so the first one says that if a and b are natural numbers such that a divides b, then a is less than or equal to b. So that kind of makes sense. Let's just think of some examples. 5 divides 10, and 5 is most definitely less than or equal to 10. Well, 4 divides 12, and 4 is less than or equal to 12. Okay, seems to make sense. Now let's look at this next one. So we want to assume that a divides b and c divides d, and then we'll show that ac divides bd. So again, that's another nice warm-up type problem. Then finally, here's this variant of the division algorithm. And this variant puts the remainder between negative b over 2 and positive b over 2, instead of between 0 and b. So let's see what it says exactly. You want to show that if you've got natural numbers a and b, then there are unique integers q and r, such that a is equal to bq plus r, where r is strictly bigger than negative b over 2 and less than or equal to b over 2. Okay, so I would say maybe try to do this third one without looking at the proof that was presented for the normal division algorithm, just for practice. But if you get stuck, go back and look at that proof, and that'll get you out of being stuck probably. Okay, that's a good place to stop.